Hello everyone. In this session, I'm going to talk about how neural networks can be used for the classification purposes. So, one thing when we are saying classification, we can do either a binary classification or we are talking about a multi-category classification. So, the classification of data can have either two categories, in which case it is called binary classification, or there could be greater than two categories, in which case it's a multi-category classification. And couple of other things, the response variable in this case is always a categorical variable, whereas your explanatory variables could be either categorical variables or numerical variables, but your response variable definitely needs to be a categorical variable. And we already know from the conceptual aspects that the neural networks can very well be used for both the kinds of supervised learning programs, both for classification purpose as well as for numerical prediction purpose, right? The neural networks can be used for both these areas of supervised learning. So this is where in this session I'm focusing only on how neural networks can be used exclusively for the classification purposes. And the next session will take about how we can go ahead with the numerical prediction, which comes under the heading of neural networks regression models. Right? So let's get started here. So the first point before I start with the 5 models under the neural network classification problems, I would like to bring out a few important points which you have to keep in mind across all the models. Whatever the models that we are developing, not just with neural networks, any other predictive models that we are building, using any other techniques, whether it is decision trees or neural networks or right support vector machines, for that matter, any kind of technique that we are using for building predictive models, there are a few important points that we have to keep in mind. So that's one thing I'm going to discuss at the beginning. And then the importance of standardization in case of neural networks. Why should we really perform standardization? Important advantages of standardization while building the neural networks. So, and what are the different forms of standardization that we have to use? So, all these things I would be discussing here. And once we get that basic idea of the different forms, then I will start off with the 5 different algorithms. Of course, for each process, as I have told you earlier also, there are so many algorithms that are designed. But let's look at 5 of these algorithms. Resilient backpropagation with backtracking, without backtracking. Then we have a smallest learning rate algorithm. Then we talk about probabilistic neural network and multi-layer feed-forward neural network. All of them are used with the same objective, which is the classification of the data. Now that's the reason what I really wanted to look at is, I'll take one single data set. Because this is a classification problem, I thought I can take up the binary classification problem. So I am taking the data set which is diabetes, which is available in various public sources. So just looking at the data set, and based on the data set we'll build the objective, and using that objective we will create the models across all these, applying all these 5 different algorithms. So coming back to the data set, so the data set is present in this location on my system. So I'm loading that data set. So if we look at the dimensions of this data set called diabetes, It's almost 600 rows and 7 columns. And I can look at the first few entries of this by typing in head diabetes. So basically it talks about the diabetes of a person, whether that particular person is positive to diabetes or negative to diabetes. Positive is there is an indication of diabetes, negative is there is no indication of diabetes. And we are talking about this diabetes for pregnant women. So the month of pregnancy, then we are talking about the glucose levels, the pressure levels, the mass, the pedigree, and the age of the person. We really want to see to what extent all these 6 different variables are influencing the diabetes. How can I link the diabetes of the person with respect to all these various variables? So this is what I wanted to understand using the neural networks, right? So we will get started with the process with this data, right? Once we get started, we will use this particular data of 600 records to build our 5 different models and try to understand how each of these models are really performing on the data set. Now, getting across, before we build any of the models, I want you to have a good understanding of a few important points. There is nothing called the best model, right? Now, we know we can use decision trees for classification purpose. We can use support vector machines for classification purpose. We can use random forests. We can use neural networks. We can use many other techniques for uh, building a model associated with classification. But let me tell you again and again, it's always a challenge. There is nothing that says this model is the best for this data. So even if I have 20 models, 50 models, it's better that I execute all the models, and based on the execution I evaluate which one is better than the other, especially in the context of the data that I am using. So there is no way I can really narrow down upon a single model which works in all situations. So if that's the case, it's better that I could have learned only that model rather than spending all my time in terms of learning as many models as possible. So there is nothing called this model is the best in all the cases. This model is always better than this model. There is no way I can make out. So it is more and more specific to the data that we are working with. So in that context, I have to really look at the models and try to execute as many models as possible, and finally narrow down on the one that is coming out to be the best within the context of the data. So always have a kind of a model transition matrix, make a tabulation of the results of all the models, determine which models are performing well under specific conditions, and based on that choose that particular model for a given condition. So that's how we have to go ahead. There is no way I can say that this model is always better than all other models. There is nothing called the best. This is the universal mantra I want you to keep in mind before going ahead with any kind of data modeling exercise. Then, understanding this terminology called standardization, though we can use in various other contexts, whereas in the context of neural networks, it makes a lot of importance. There's a lot of significance for this world of standardization. So all the input values, now I have shown 7 different variables, out of which diabetes is a kind of a response variable, whereas the 6 others are typically the explanatory variables, or I'll call them as input variables. Now what the process says is, it's a good practice to standardize all the external input values before passing them to the neural network. So the first step is try standardizing all the variables. all the values of the variables before you start implementing the neural network algorithm on the top of it. So in our case, they are all not standardized. So which means before I call the neural networks algorithm, I have to make sure that all the input variables are standardized. The reason is if I am not done the standardization, large input values, if a particular input value is large, look at from the data. Now I could see the glucose is a very large values, 100 plus values, whereas pedigrees are much below, where majority of them are in single digits and some of them are between 0 and 1. So we find a complete variation in the length, in the size of the data, right? Large input values, they will carry small weightage factor and vice versa. This is what will have a very biasing in the kind of a result that we are getting. So it's better to make sure that the size does not matter. By doing this standardization, we are bringing almost all the elements into a similar range itself. So the inaccuracies introduced by very small calculations if I am not doing the standardization, and even the changes that are getting made. We know that in case of neural networks, there is a kind of a continuous learning process. So the algorithm keeps on changing, and the changes that are made to the algorithm will be very minute, which means the number of iterations that are executed will be much higher, the learning rate would be much slower in the process. So it's always advised that when you are executing neural networks, better do a standardization of the data and then give those standardized data as the inputs to the neural network algorithm. And when we are talking about standardization, there are different ways. This is every observation you subtract the minimum value and divide it by the range, which in a way will keep all the observations in the range of 0 to 1. Whereas this is you are subtracting the mean of the observations and dividing it by the standard deviation. This is directly executed by a function called score in R, and this is nothing but it is computing the Z score, which is more otherwise called as a normalization of the data. Whereas in this case, every observation we are dividing it by the square root of sum of squares. Even this way we are keeping the observations very much in the range of 0 to 1. And here also we are dividing it by every observation by the maximum plus 1. So that way again we are bringing all the observations within a specific range. So though all four of them can be used, this because this is straightforward in R, we will think of using this transform, but otherwise you can very well play around with the other transformations also and use them for the data as long as they are producing much better results compared to your Z-score transformation of the data, right? So with this as the input, I think we are in a position to get started with our first neural network model, which is the resilient backpropagation with the backtracking mechanism. And that is executed in the package called NeuralNet with the function called NeuralNet. So let's install the package. Along with that, let's try running the function to see what all flexibilities do we have in terms of execution of this particular model. So first let me install the package. I think it should be there in my system, but the first one, let me install it, NeuralNet. Okay, let it install the package. Alright, the package is installed. So let's load the package. Alright. Now let's try looking at what is there as a part of the neural net function, so that we can see what all are mandatory and what all are optional, what all kinds of variations that we can create when we are building the model. Trying to understand neural networks is used. Neural net is used to train neural networks using back propagation. So that's the method. Resilient back propagation with or without backtracking. So we have these two methods here. Now we are discussing the resilient back propagation with backtracking, and in some cases I can talk about resilient back propagation without backtracking. So both of them we are going to discuss. Are the modified globally convergent version, which is otherwise called as the smallest learning rate, even that is there as a part of our understanding out here. The function allows flexible settings through custom choice of error and activation functions. So here we have a custom choice. One is the error functions, we have a choice, and the activation functions, we have a choice. We have already discussed about different kinds of activation functions, though most commonly I can think of using a sigmoid function, but there are a few other activation functions which I have a flexibility in terms of applying. So let's see what all we can do. Neural net formula. The formula for me, I know in this example, the formula that I am going to look at is the diabetes, which is my response variable, tilde dot. These are all my explanatory variables. So here the formula is very much fine for me. Data is a data frame of the variables which we have. I can provide the data frame of the variables that are specified in the formula. Hidden. Now this is one aspect. A vector of integers specifying the number of hidden neurons in each layer. I have to specify how many hidden neurons are there in each layer. So if I am having one layer, I can very well specify how many hidden neurons are there in one single hidden layer. But if I have two different hidden layers, I have to specify it through a C function. C2, 3 means there are two hidden layers in the first layer and three hidden nodes in the second, three hidden neurons in the second layer. So that is how I specify hidden equal to C of 2, 3. Then the threshold is talking of the threshold for partial derivatives of the error as a stopping criteria. By default it is 0.01, but if I want to specify a different limit which is even more lesser than this, I can very well specify that. Then there is a step max, which talks about the maximum steps for the training. So once that by default it is 100,000, but if it crosses, probably the algorithm will stop. Then number of repetitions, by default it's 1. I think all these can very well be set as a default. Learning rate factor, learning rate, right? Life science step, algorithm. Algorithm is rprop plus. Rprop plus is an indication of with backtracking. Right, we are talking about resilient back propagation with backtracking. I'll specify it as rprop plus. But of course, if you see this, it's a string containing the algorithm type to calculate the neural network. So I can give either backprop, rprop plus, which is resilient back propagation with backtracking. This is for without backtracking. SAG, we are talking about globally convergent algorithms. or even SLR, which is the smallest learning rate, also talking about the global convergent algorithm. So we can actually give all these 5, but here I am looking at these 3: RProp plus, RProp minus as the next algorithm, SLR as the next. So backprop is referring to back propagation. RProp plus and minus are resilient back propagation with and without backtracking. And we are talking of SAG and SLR induce the usage of modified globally convergent algorithm GRProp. So these are some of the things that we are very much giving as the input. Then we are talking of error. So we said there is a flexibility in terms of giving the error. So we can very well specify SSE or CE. SSE is an indication of sum of squared error. If required, I can very well specify the default is SSE. Right? We can specify either SSE, which is the sum of squared error, or CE, which is nothing but cross entropy. So these are the two ways in which the error is typically computed. If required, we can very well play around with that. And the activation functions. If you look at the activation function, by default, it's a logistic function. Whereas, if you look at the activation function, it's a differentiable function that is used for smoothing the results of the cross product. So you can use either logistic, which is the default one, or tan h, which is the hyperbolic tangent. So I can use either of these two to build my model. So basically these are the kind of explicit things that I have, which I can play around with. And once our data is ready, I think we should be able to implement that model with our data and finally see which algorithm with what kind of error functions and activation functions we are able to do a good job on our data. Right? So let's get started. So we have already loaded this NeuralNet package, got the data, right? We know that the response variable is a categorical variable. In this case, I have gone one more step ahead and ensured that it and looked at that it is a binary variable, only two classifications. Now examine the data, look at the summary, see if there are any NA values or something. So let me do a summary of diabetes, which shows yes, NAs are there. Right? If you look at glucose, there are 5 NAs. Under the pressure column, there are 28 NAs, and under the mass column, there are 9 NAs, which means some values are missing from the data. So it's better that I ignore them. I work with only with the remaining set of elements. So this is where I'll say diabetes Na dot omit of diabetes. So those rows which have at least one missing value in the observations collected, I'm deleting that entire record. So I'm left with only those records where all the data is present for them. All the patients for whom the full data is present. So if I quickly want to check now the dimensions of diabetes, I could clearly see now it's only 564 rows and 7 columns, means 36 records got overall eliminated from the process. And in the process, now I can again relook at the summary with this 564 observations. Now I don't see any kind of NAs under any of the categories. So these are the 574 that I would be using for the working of my model. So I have examined the data, I have looked at the summaries, etc. And this is how my final data is in place. Right, I have kept my final data in place. Now I have to convert the response variables. Now we know in this diabetes, if I quickly look at the head of diabetes, I could see that the first 6 are the explanatory variables, and the 7th one which is the diabetes, is actually a scale, is actually a factor variable, which is the response variable. Now we will simply consider, in this case, one important thing that I have to set is make sure that the response variable has values 0 and 1. I have to convert them into zeros and ones so that I can do the scaling process here. Because we have a scaling process in place, I am making sure that the response variable is also converted into zeros and 1. So that's where the negative I'll set it as 0 and positive I will set it as 1. So let me do that. Diabetes $diabetes, I will set it as if else $diabetes, if this is equal to POS positive, then set that value equal to 1, else set it equal to 0. I think this one single line is sufficient for us. So let's quickly check the head of diabetes now again. The head of the diabetes, now it is showing either ones or zeros. So now we can actually go ahead in terms of doing the scaling process. Right, I can very well go ahead in terms of doing the scaling. So we'll simply replace it, probably diabetes 1 we will call, so that we'll have both of them. Diabetes 1, let me simply call it as scale of diabetes. Right, I have scaled it, means the scale function will subtract the mean of that column from each of the observations, and the resulting value will be divided by the standard deviation of that particular column. If you quickly look at the head of diabetes 1, you will see that the size is almost immaterial now. All of them are within a simple range. The size is very much immaterial in this case. So that is what we are doing. And once we have done with that, the next step is make sure that the whole data is being split into a training set and a testing set. So we really want to make sure that the entire data is split into a training and testing. 70% of it I will put under the training data, 30% of it I will categorize under the testing data. So we have already seen that there are 564 observations altogether. So I'll take the 70% of that, which is approximately 395. So 395 observations, I'll take it under the training data, and the remaining ones I will take it under testing. 564 minus 395, 169 will be there as a part of the testing data. 395 will be there as a part of my training data. So to generate that, first let me set a seed. I'll set a seed to some dummy number, which is 1000. Then I'm creating a variable called train, which will randomly select some 395 observations, 395 values between 1 and 564, so that those 395 values that are being selected randomly, I would use those rows as a part of my training data, and the remaining rows I'll be considering as a part of my testing data. So for that, to select randomly, I'll use a function called sample, where I will select from 1 to 564. I will select some 395 values at random without any kind of duplication. Without any kind of a duplication is executed through replace equal to false. So this is how my training set comes. right? So these are the numbers. So probably if I have to quickly check what is there as a part of the train, we get some 395 numbers randomly between 1 and 564. So 185, 428, 65, these are the numbers between 1 and 564, and the total number of numbers are 395, and there is no amount of overlap between the numbers. Now these rows, I will take them as a part of my training data. So that's where I am calling it training data. Train data is the name of the variable, which is a subset of diabetes 1. So from the diabetes 1, I am taking a subset which contains those rows which are there as a part of the train, and it will contain all the columns. So that's where comma black. So this is my training data, and now I also have my testing data, which is also a subset of diabetes 1, but this will not contain the train, the values which are there as a part of the train. So that's why representing it as a minus train, and it will contain all the columns. So this becomes my test data. I have my training data, I have my test data. It's better that I create my formula also, right? For creating the formula, it's better that I get the headings. Here I have those headings. So I'll say diabetes is my dependent variable. Tilde, I'll take all the variables out here, right? Pregnant, glucose, I have to consider all the variables as my explanatory variables. So I want to try to build a neural network between this. So this becomes my formula at this moment. So okay, so I am talking about the storing of the form of the model, so which I have already stored it as a part of F. I have broken the data into training data and the testing data. Now I can very well fit the model using neural network. Now here some alternatives that are there. I can change the hidden neurons, right? Some variables or some kind of flexibilities that I have. Hidden neurons I can change. I can change the activation function, and I can also change the error function. So there are the three things that I can very well change. So here I can set them to any number of values. Here I have either sum of squared errors or cross entropy. Here I have by default logistic, or I can also go with a hyperbolic tangent kind of a function. So these are some of the flexibilities that I have. So let me go ahead in terms of fitting different kinds of algorithms. So let me say fit uh, rprop plus, I'll call it as fit rprop plus, and I have to specify the hidden neurons as well as the error activation function. So if I look at, now this is only rprop plus that I am going with, so I'll continue with that rprop plus, but I'll say error function SSE and activation function logistic. So let me call this as SSE logistic. I'll call it as SSE logistic with one hidden neuron. So these are some of the things I'm trying to fit. So I am creating a function called NeuralNet, wherein my formula is F. I have a data which is trained data here. Now I can very well set hidden neurons. Initially let me set them to 1 and let me improvise the model, and algorithm I can very well set it as rprop plus. This is my algorithm. Now I am not changing the activation functions or even the error function. So that's where I am leaving them to be by default. So this is how my neural network model got built. Now what I'll simply do is I'll change the hidden layers 1 2. So this is one model that I have built. Let me change it to 3 to build one more model. So this is one more model that I have built, and let me change it to 4 and 5 as well. So I'm building different kinds of models, one with 4 hidden neurons and probably one with 5 hidden neurons. Again, I'll do it only with one such thing, and the remaining you can very well take them forward. So this is one part. Now let me do with the same 4 or 5, but this time let me change the error function from SSE, let me change it to CE, which is the cross entropy part. So within this, I want to set error dot FCT is equal to C. This is one algorithm that I want to try with 5 different itself. Okay, the response is not binary. So that's where, okay, CE is not working out here. Okay, the response actually has to be binary, which means I should not have transformed the response variable. Because I have transformed the response variable out here, I'm not able to use this CE. So had I kept the response as binary itself, then I could have gone ahead using the cross entropy. Fair enough. So here we will use only the sum of squared error. So let's not look at the CE part here. Whereas one more thing with SSE, I can also work out with my activation function, which is the tan H. So let me call, instead of logistic, I'll put it as tan H. So here, instead of error function, I'll call act FCT, and this I am setting it to tan H. So we are just creating different kinds of models. We really want to check out in which case the model is working much better. So we have created different kinds of models. Now the next part. So if I go back to my data, so this part, my material, this part is executed now. I have changed the hidden neurons. There is an option for me to change the activation function as well, and even the error function. So we have just played around with all these things to make sure that we have created different kinds of models which you can very well evaluate each one of them separately. Then we are talking about a print method to give the overall overview of the model. So I'm taking the print. Let me give one by one. Print of the first one. So this is how the model got executed. The first model. Right, we'll just go to the top to understand it. The print is giving complete details of the model. So there are a good number of iterations that are happening. Right, it has called this particular formula. The response variable is this one. Right, so we are talking about now, when you look at the way it got progressed. So the covariates, we have supplied it with 6 different covariates. Now within the model, you could see different kinds of functions being computed. Right, now the activation function is, it has gone ahead with the logistic, so that's where it is calling it as 1 by 1 plus e to the power of minus x. The error function is sum of squared errors, so that's where y minus x whole squared by 2, sum of the squares of the errors. Then it has taken the different observations, all the various observations that are there as a part of the training data. some kind of a learning is being performed at each and every step, and finally the weights are computed. There is a kind of iteration. So initially these are the initial weights, and after that the weights are getting modified. There is a kind of iterative process that has finally gone, and this is what is the final result matrix that we have got. The error is to this extent. It took 733 steps to improvise and optimize the model. There are a few important aspects coming out to each of the hidden layers. Intercept to hidden layer, pregnant to hidden layer, each variable to the hidden layers are being computed, and that is the how the whole neural network got built. Now let's see, let's try a couple of other stuff. If I go with the tooth, so we see that another separate kind of another separate model is created here. It took 3867 steps. The error came down to 123, whereas in the earlier case the error was to the extent of 129. Now if I look at the three hidden neurons case, error came down to 106, but it took 6894 steps. So the learning is becoming very heavy, but the error is slightly coming down. Going with 4, the error has actually increased to 107 instead of 106 in the earlier case. Now the error went up to 107. Now what if I have tried going with the 5 variables case, error came down to 94. So the 5 variable is looking much more appropriate, with the training error coming down, it taking approximately 6500 steps, and this is how the tree is, the network is finally getting built. But at the same time, now instead of logistic, I have also built the TAN-H model. So let me see what has happened to this TAN-H model with the 5. The TAN-H model is having an error of 105. So overall it looks like at this moment it is looking like the logistic activation function, which is the sigmoid activation function, along with SSE, sum of squared errors as the error function, and 5 hidden neurons, is doing a good job in the RPROP plus category at this moment. So we have looked at the print to get this kind of an understanding. Then, so in this case we are able to make out what is the error and how many steps it has actually taken to reach a particular threshold value. Now I can very well plot the models also, right? I could have easily plotted the models. So I'll take out my output so that I can plot them. So let me do the plotting of the first model. So this is not TAN-H, this is logistic 1. So this is the plot of the model. Our 5 inputs or 6 inputs, they got these kind of weights. They became one hidden neuron, and this hidden neuron is mapped to the output called diabetes. This has produced an error of 129, and the whole weights they were created in 733 steps. Now let's look at how the two hidden neurons case looks like. So these are the mappings, 6 variables, each of them how we have linked them with 2 hidden neurons, again with a kind of a repetitive process, making resulting in an error of 123 and taking 3800 steps. Similarly, now when I have to go ahead with the 5 case, this is how the 5 model got built. Very complex model, difficult to interpret. difficult to explain, but that's how the neural networks go ahead. And from our perspective, our focus should be in terms of understanding whether the predictions are coming out proper or not. Right? To what extent the model has been able to do the learning properly. Now, when I run this model on the test data, what is the level of accuracy that is coming out with respect to the model? Now, let me also use the tan H5 on this to understand. Okay, another model got created with 9392 steps, resulting in an error of 104. So that's how we have different kinds of models at our disposal, right? So I'm seeing that the weights, estimated neuron weights at each of the cases are being displayed in the process. So that entire thing is becoming a very complicated kind of a structure, but that's how the hidden neurons will try to learn from the input data and try to make sure that the classification of the records is done more and more appropriately, right? And once we are done with this part, once we have got the models in place, now we will use all these methods that we have, and I'll also use a method called compute. Here we don't use the predict, we use the compute method, right? We'll use the input wise, we'll use the compute method. So let's see what this method is. How is this slightly different from the predict? Compute is a method for the object of class NN. So we don't have a predict method for the object of class neural networks. So we have to use compute. Compute the output of all the neurons for specific arbitrary covariate vectors. So input wise I have to give only covariate vectors. So I can't give the response variable as an input. Please make sure that the order of the covariates is the same in the new matrix or data frame as in the original neural network. So the order has to be the same. So here I have to give compute x. X is a kind of object of the class neural network, which means our model can very well be used here. Covariate containing the variables that have been used to train the network. I have to give only those variables which have been used to train the neural network, and an integer indicating the neural network's repetitions which should be used. I am not, by default it's 1, there is no kind of a repetition in the process. And the output wise it will give me the neurons, the list of neurons output for each of the layers, and I also get the net result. Net dot result is containing the overall result of the neural network. So these two things I need to understand. It's not one single output, I'm getting two different outputs out here. Whatever. So let me go ahead in terms of doing the prediction now, right? So we'll go with pred. Let me use pred and this name, right? I'm predicting it with one hidden neuron. I'm using a function called compute where this is the model, and along with that model I have to give the testing data. So let me call test data, but I will give all the rows, but I'll not give the seventh column as an input to it, because seventh column is the output for me. So I'll not give the seventh column as an input to it. All the remaining inputs I am very much providing to it. So this is how I'm using my model for doing the predictions. So I have predicted it with one case, the model with logistic model with SSC as the error and with one hidden neuron. Now I have predicted using the two hidden neurons model. Again I am doing the prediction with three hidden neurons model, four hidden neurons model, then we are going ahead with the five hidden neurons model. Along with that we have also created one more model which is the tan H with 5 model. So here instead of logistic activation I have used the TANH activation, but of course I did not use the TANH for all the hidden neurons. I have gone ahead only with 5 hidden neurons, but actually I could have tried all the possible combinations. So basically I have got now 6 different predictions coming out of each of the models. Now let me see the output wise. Just let me type one of the output. We will get a clarity on how the output is structured. So let me copy and paste this one. So here if you look at the output, there are a few things that are coming out here. Where is my output? Yeah. If you look at here, first thing it is giving me the neurons, right? All the different neurons for each of the variables. It has given me the neurons, but look at the next one, which is, so this is the second neuron set. Now you could see here the net dot result. So the net dot result is actually, in some cases it is positive, in some cases it is negative. Right? The net dot result is actually coming out to be this, which is the positives and the negatives. So what you can very well do is, you can very well look at, if it is less than 0, you call it as, if it is less than 0, you call it as negative. If it is greater than 0, you call it as positive. Right? So that's one thing we can do. So what I can very well do is, if else, so I can very well set this value, this predicted value, right? I can take this predicted value, or I'll create another variable. Why should I take a predicted value? Here I'll take it as pred1. I'll call this as pred1, where I'm taking from this prediction $net dot result, right? I'm taking net dot result. If this particular value, right, from this particular prediction, I'm looking at net dot result. If it is less than 0, I'll call it as, so anyhow we have set them as zeros and ones, right? Less than 0, let me set it as 0, otherwise let me set it as 1. So that's what I am calling as pred 1. If the net dot result is coming less than 0, I'll make it 0, otherwise I'll keep it at 1. So that's how I got my pred1 result. Let me quickly look at it. So I have got the numbers either zeros or ones. Now I can very well compare them with my test data. So I'll do a table wherein from the test data I am considering the diabetes column, which is the actual, and based on that I am also considering the pred1, which is the predicted. Based on this, dollar operator is invalid for atomic vectors. Okay, let me consider it instead of test data dollar diabetes. I'll put test data 7th column. Yeah. Okay. Oh, okay. This is this is a problematic stuff. But anyhow, the minus and 0, they are also okay. Let me do one thing then. Even the test data dialer diabetes, I'll set it to 0 or 1, right? So I'll say spread act 1, actual 1. I'll put if else test data dollar diabetes is less than 0. I'll call it as 0, otherwise 1. So otherwise I can put it instead of dollar diabetes test data. Let me take the 7th column value. If it is less than 0, I'll call it as 0, otherwise I'll call it 1. So now I'll take a table between the pred one and actual one. This should be better. I'll take the table between pred one and actual one. So we are getting the 77 which are correctly predicted, this 48 which are correctly predicted. So out of 169, we are having 125 of them correctly predicted and 44 of them are wrongly predicted. So the accuracy in this case is 125 out of 169, resulting in a 73.96% accuracy, which is meaning that around 24% is the error rate when we are going ahead with one hidden neuron model. Right, one hidden neuron model, when I'm testing it on the testing data, the error is approximately around 24%. Now let me check out the others. Right, let me quickly look at the other ones where I will go with prediction 2. So I'll continue with pred 1 itself, but I will look at this particular result, logistic with 2 hidden neurons result, right? So this will show me either 0 or 1, right? Now I'll do the table directly. So these two steps are sufficient for me. I'll make the table between pred 1 and actual 1. So here it looks like the accuracy is only 119 with 50 being the error. So 119 out of 169 is the accuracy when I am going with two hidden neurons kind of a scenario. So on the test data, the accuracy of the two hidden neuron scenario is only to the extent of 70.4, which is 29.6 is the kind of an error rate. And how about if I have gone with the three hidden neurons model? When I go with the three hidden neurons model and go ahead with the table part, so here it is coming out that only 116 is the correct prediction, with 53 being erroneously classified, which means this model is also not that superior compared to our one hidden neuron model for this example. Similarly, now when I go with 4 hidden neurons case with the same logistic activation function, and after that executing the actual versus the predicted, in this case it is 118, which is also much lesser compared to the one hidden neuron case. Even this is to the extent of 70% accurate. Now what about the 5 hidden neuron case? So RPROP plus algorithm is only giving me the advantage to this layer itself. So in this case it's again the same. 106 is the only accuracy out here. So there's a lot of overtraining or overfitting that has happened on the data, looks like, because on the training the error is much minimal when it was a 5 hidden neuron case, whereas here the error is looking much higher in case of 5 hidden neuron. Then what about going away from logistic to a hyperbolic tangent model for doing the same prediction part? Let's just check if there is any improvement. Yes, here it is. 123 is the accuracy on the testing data and only 46 is the error rate. I mean the misclassification. Looking at around 72.7% being the accuracy out here, but which is also slightly lesser when I compare it with one single hidden neuron model in case of RPROP plus. RPROP plus with one single hidden neuron has given this kind of an advantage for us, especially with this kind of a data that we have worked out with. Right? So that's how we are looking at trying out different kinds of models and testing it out on the testing data to see in which case the accuracy of the model is coming out to be much appropriate. And that would have been a most choice model for us in terms of the implementation part, right? So that's one part we have to be very much understanding. Probably I might have got a better accuracy on the same data with the same training set and the same testing data set, especially when I have used decision trees or I had used some other mechanism. So I have to be slightly appreciative of the fact that there is no one single model which I can consider it as a best model for this kind of a data. So right now around 74% is the kind of accuracy that we have got to the core when we have worked with RPROP plus algorithm, which is the resilient backpropagation with backtracking. Now I want to look at the same six, or probably I'll look at the same six with RPROP minus, which is resilient backpropagation without backtracking, and probably with the smallest learning rate kind of a model. Or I will like to leave those things to you. But here I will look at that particular model which has given me the best possible output in case of RPROP plus, which is the hidden neuron equal to 1. I'll only consider that hidden neuron equal to one example, and I will try to execute RPROP minus as well as the smallest learning rate, both the algorithms on the top of that, because the next two, the resilient backpropagation without backtracking, the only difference that we are making is we are making a change to the algorithm. We are changing it from RPROP plus, we are changing it to RPROP minus. If you want, you can read through this entire stuff. The whole process is the same in the resilient backpropagation without backtracking. So there's no point for me to go through the slide again. Probably I can very well implement the same in R, especially with I can do two things. One, I can execute it with hidden neuron equal to 1, and the one that came in the second place on our testing data, which is the scenario where we have used a tan H activation function and hidden neurons equal to 5. So we'll try both these models, and on the without backtracking as well as on SLR, and try to see which one has produced what kind of a result. Right? So let me execute all four of them together. So here also you could see that the difference is only to the extent of SLR out here. Otherwise the whole model remains to be the same. So we will go ahead in terms of doing those four models now, which will cover the two different techniques as a part of this particular course. So let's execute those four models and then see if there is any kind of an improvement in the overall prediction process for us, right? So there is no need to make the changes to the data. Everything is there in place. So now let's take fit RPROP minus, and SSE is the only error that I am considering. So I'll take it as logistic with 1. This is one model I want to fit, wherein I am calling it as NeuralNet Function. F is my model, right? So I don't need f dollar. F is my model. Data is my training data. Then the hidden neurons, let me set it at 1. Then algorithm, right now let me set it as r prop minus r prop minus, that's the algorithm. And hidden is 1, fair enough. So this is one model, right? Activation function act.fct, that is the activation function looks like. Let me just quickly check. Yeah, it is act.fct. act.fct. I can either set it to logistic or tanh. So by default anyhow is logistic, but anyhow let me just set this. So this is what I am creating as the first model. Right, this is what I am creating as the first model. Then I am also going with instead of r prop minus, let me execute SLR. So algorithm, I'll change it to SLR with the same hidden one layer, and instead of r prop minus, I'll call it as SLR. So this is one model that I wanted to build, and two more models that I am interested in building. Instead of logistic, here I want to change it to tanh activation function. Algorithm, let it be SLR. The hidden layers, I'll set it to 5, or probably I'll set it at 1 itself. Why do I need, I mean you can change all the combinations, fair enough. So instead of logistic, here I'm calling it as tanh. So this is one more model that I wanted to try. And similarly, the last model that I am interested in is again r prop minus. Though you can create as many, wherever there is a flexibility for customization, that will improve your number of options that are available, or number of models that are available for us, which will where we can actually play around with the different sets of models to have a good understanding of the increase in the accuracy of the model. Now, as I did earlier, we can do the printing process, right? If you go with the print of each one of them, you will get the error part, but let me directly take the plot of each one of them, so that right we can, or probably let's plot all four of them, right? So I'll set par mf row equal to c2 comma 2, which means the window size I'll set it as c2 comma 2, so that all four of them I can plot in the same graph, so that I don't need to really execute all of them separately. So I'm saying plot of this one, oh I have to put small p, not the capital P. Par mf row equal to c2 comma 2. Okay, so here when I am going with it, you have an error of 129 and it took 453 steps. So this is what your rprop minus logistic model has given. Then I would also go with what about rprop minus tanh1. So this is what it became. Error is still 129, but it took only 120, 204 steps out here. And now when I go with SLR, which is the smallest learning rate algorithm, the error is still 129. It took 10,108 steps to do the execution. And finally, the fourth model also, when I am going with fit SLR tan H1, this also came out with an error of 129, but it took 5,517. So probably it looks like, on the training data, almost everything has given me an error of 129 itself. Now this is the time for me to look out for the testing data so that I can do a better job out here. So I am using the compute function to work on the testing data. So this is where I am creating 4 different predictions. Pred, this one. When I am going with this spread, I am using the compute function. Within that, the model is this particular model, and the testing data is test data, wherein I am not considering the 7th column, which is the response variable. I am considering all others as a part of my testing data. So this would be the one model. Then I have another prediction coming out. The second one, I am doing the prediction, where again I am using the compute function. This is the name of the model, and this is the test data that I am using. So a model got computed. The prediction actually happened with logistic and SLR algorithm. Now I am going ahead with hyperbolic tangent with again the SLR algorithm. So I am fitting that particular model to this test data again. So this has given me another prediction, and the fourth model that I have fitted, rprop minus the resilient backpropagation without backtracking using one hidden neuron and hyperbolic tangent activation function. So based on this, if I am trying to do the prediction, this is how the prediction is working out for me. So these are the 4 predictions that I have. Now I will always set pred1, which is if else this particular value, if it has come out to be negative, I'll set it as 0, otherwise I'll set it as 1. So pred1 logistic $net dot result. If this value is less than 0, I'll set it as 0, otherwise I'll set it as 1. Similarly, I'll do a pred2, which is again, I'll set if else, the second one, pred fits SLR logistic 1. Then we are talking of $net dot result is less than 0. I'll set it as 0, otherwise I'll set it as 1. Okay, pred2, this side is what I have to set the arrow mark. Similarly, now I'll set pred3, which is the prediction value from the third one. So I'm setting if else. The third model that I have fitted is this one, $net dot result. If this one is less than 0, I'll set it as 0, otherwise I'll set it as 1. And finally, I also have my pred4. So 4 predictions, all the 4 predicted fitted values, I am simply changing them and setting them as either zeros or ones. Right, this is my 4th model. If this is less than 0, I am setting it to 0 or 1. So these are the four predictions that we have. So let's create a table between actual one which we have created earlier and pred one. Actual one is nothing but the actual values have been converted into zeros and ones. So here the table is telling me the accuracy is to the extent of 77 plus 48, which is 125. Going with pred 1, the accuracy is 28, 125. Pred 2 also resulting more or less in the same. Pred 3 also resulting in the same. And even the pred 4 is more or less the same. So with respect to one hidden neuron, whether I'm going with SLR, or so when the hidden neurons are actually increasing, again the algorithms, whether we are using rprop plus or rprop minus or SLR, they will have a very big impact in our on the building of our model as well as the accuracy of the testing on the testing data. So as far as this particular algorithm is concerned, or this particular package is concerned, we can use the three different mechanisms from the neural net package, right? Neural net is the function, but the kind of flexibilities that we have is algorithm wise, I can set it either to rprop plus, rprop minus, or SLR. That's one flexibility. Then the error functions, I can set them to two possibilities. SSE is by default sum of squared error. Along with that, I can also set the cross entropy. Generally, when our variable is a categorical variable that we have not scaled it, in case we have not scaled our response variable, then I should look at the cross entropy as one more option for error function. Then we have also have the choice of the activation functions, which is the input variables, how they are getting transformed into the building of the model, where we have logistic as one option, which is the default one. Along with that, we can also go with a hyperbolic tangent, which is tanh, which means these all combination. And along with that, we have an option of working with n number of hidden layers. So depending on the number of hidden neurons that we are building into the model, the complexity of the model is going to grow up. But at the same time, there is a possibility that the accuracy in terms of the prediction on the testing data is also bound to go up. So these are some of the things we are very much we have to take care of while building our model and while testing the model on the testing data. Now we will move on to a completely different type of model, which is again a part of the neural networks for the classification data itself, but the approach that we are going to use for it is going to differ, right? Now let's look at the next algorithm, which is the probabilistic neural network. So slightly different from the neural net package that we have used. We'll execute it on the same data so that we'll get a clarity on how this particular model is working and what's the level of accuracy that is coming out with this particular model. So this is executed using a package PNN, probabilistic neural network, and within that we will be using a function called learn. That's the input to it. So let's load it. Let's try to understand what is there as a part of it. First, let me do the installation of the package. PNN, sorry, install.packages. Okay, we have installed this particular package. Then let me load this package as well. Library PNN. So we are loading this particular package, and then we need to understand what is there as a part of the learn function. Well, let me just close off these windows. Let me understand what is there as a part of the learn function. So create or update a probabilistic neural network. So that is what is done by this learn function, which is there as a part of the PNN package. And it requires learn. The input is set. Set is a data frame representing the training set. So I have to give the data frame containing the training set. The first column, now you see the way it has to be. The first column is used to define the category of each observation. So I have to give the data frame here in such a way that the first column actually contains the category. So whereas in our data, the last column is containing the category. So this is where I may have to change it. First of all, I have to change it in such a way that the first column contains the category. Then the other input that I have to give here is NN, which is a probabilistic neural network with or without training. Right? So I have to give the probabilistic neural network with or without training, and the category column, the field number of the category. So otherwise, if I don't have this, I have to give the field number of the category. One is by default. So that is what I have to give as an input to this. Right? I can give learn, and I have to give the name of the data frame. The first one is the category. The first column is used to define the category of the observation. So let me see. First, there's nothing more, so you don't have too much of a flexibility in the model. Right? So let's see what I have to give. I have to give the response variable y, and I also need to give the covariates that are present as a part of the data. Right? So working wise, I'm loading the PNN package, done. Getting the data into R, done. We have examined the data, convert the response. Now I have split the training data. Now I have to give a new training data altogether. So let me take the diabetes again. Let me look at the head of diabetes. Right. So now this diabetes is actually showing as 1 and 0. And now it's better that I convert it back to negative and positive. Right. So what I can do is diabetes $diabetes. I'm setting it to if else the same diabetes is equal to 0. I'm calling it as negative, else I'm calling it positive. Right? If the value is 0, I'm calling it negative, otherwise I'm calling it positive. Okay, the equal to I have set to set it with a double equal to. So now again when I check the head of diabetes, it comes out like negative positive. But let's look at the structure of diabetes. Now it might be looking like this one is a character with positives and negatives. So this is where I have to convert it into a factor. So what I'll do is again diabetes $diabetes, instead of being a character, I'll do it as dot factor of the same. And now when I look at the structure of diabetes this time, it's coming out that it's a factor with two levels, negatives and positives. So now I have to bring the last column to the first column. That is the aspect that I have to work with. Right? So I have to give I have to bring it to the first column. So let's say diabetes. I'll do a C bind where the first thing I'm taking is diabetes $diabetes. Right? I'm doing a C bind diabetes $diabetes, and to that I'm actually binding diabetes. So once I do this kind of a C bind, let's see how the diabetes is coming out. So I'm binding the that column to the first, so I have it in the first as well as in the last. Now I'll remove the last column. So I'll say diabetes, a subset of it without the eighth column. So now I could see, if I am looking at the head of diabetes, I am getting it exactly in the same way that it requires a data frame where the first one, okay, it is coming out as diabetes $diabetes, right? So let me change the name. So I'll say the names of diabetes. If I look at the names of diabetes, it's coming out as this one, right? And I can check the names of the diabetes for the first one only. When I say names of diabetes first one, it is coming out to be this. So I will assign this to diabetes. I'll assign this to diabetes, which is in quotes. So now let me look at the names of diabetes after this assignment. Okay, the first column is coming out as diabetes, pregnant, glucose, etc. So this is how it looks like. Our values need to be there as a part of the probabilistic learning neural network, because it is taking a learn as a set, and set is a data frame representing the training set. And in that training set, the first column is used to define the category of each of the observation. Category of each observation. So this should be sufficient as an input. Now I have to break the data into a training data and the testing data. For that purpose, again I can do the set.seed. I'll do the same 1000 train. Again I'll pick up the same from the sample. I'll use a sample function to pick up between 1 to 564 some 395 values randomly, where the replace is set to false, means there is no duplication in the picking up of the values. And train data, I am taking it as a subset of diabetes. I am taking a subset of diabetes which contains the train rows and all the columns. And test data also I am taking a subset of diabetes which contains minus train rows, means which does not contain the rows that are there as a part of the train, and it contains all the columns. So this is where I have split the data into the training data and the testing data. The model is already there, the F, but now I am not much bothered about the model. Now we can very well do the fitment of the model. So because there is only one fit PNN, I don't have any other variations in that, so I'm just taking a base model. I'll use the learn as the function name, and now if you see, it's sufficient that if I had given the S set, right, I can very well give the set, and the first column is used to define the category of observation. So the set is sufficient, looks like. So let me give set equal to, and I'll give the name as diabetes. that looks like sufficient for the model. Yes, the model has been fitted, right? Nothing much. Now if you want, you can type in the name of the model to see what it has given. You could see it has done a few things based on the, oh sorry, I can't give diabetes as an input. Let me redo the model. The set is the train data for me, right? It's not diabetes. Set is the train data. So this is the new model that I am building only with the training data because I want to test it out on the testing data. So now when I am doing a fit PNN, so this is what the model has actually executed. So let me quickly look at the model. So the model is probabilistic neural network. So this is the data set which it has fitted. So you will get all the 395 observations. The category dot column, by default it has taken the first category. The categories that are there in that column are negative and positive. There are 6 explanatory variables that are being used for building the model, and the N is saying there are 395 observations that have been used to build the model. So these are some of the various attributes that have come out of the model. And when you are looking at the summary of this particular model, right, there is in the summary you are getting that it's a model where the set is a data frame of 7 different columns. Category column is the first column, and there are 2 categories in that column, negative and positive, and the K as well as the N, which is K talking about 6 different independent variables or explanatory variables, and N talking about 395 records being used to fit the model. Now the next important aspect here, right, okay, model is fitted. We have looked at the different attributes of the model, and we are getting the different contents of the fitted by going ahead with the dollar notation, or probably once I have typed the name of the neural network, I have got all the various things that come as a part of the output. I have looked at the summary method, getting some details about the model. Now the important aspect is I can very well use the smooth method, and I can very well get the smoothing parameter here. Now let's look at what is the smooth method out here, right, to get a clarity. I am talking about a smooth method in PNN package. Smooth is a method work around the smoothing parameter, wherein I have to give the neural network, which is a trained neural network, as the input, right? Sigma is the most important. It is optional, which means the system can generate the sigma value for us. If the value is already known, it sets directly the parameter and do not search for the best value. But if you don't set it, it will do the searching for the best value. So it's more of a smoothing of the overall parameter for building the neural network. So once you have the data with you, once you have the fitted model with you, sometimes we get into the process of smoothing. So we'll say fit smooth, which is nothing but I am using a smoothing function smooth, where the parameter value will get smooth, and I'm using the fit PNN as the input to it. So loading the required package. So this requires rgnoun as the package. Could not find the function rgnoun. So we have to install this package as well. Now let me see if this works. Yeah. Now the smoothing is typically working. It requires this package RG node. We'll do the smoothing of the parameter to finally understand what is the level of fitment of this particular model. Okay, so there is a smoothing that is being performed. If you look at the output that got performed out here, so there are the data type is floating. So the operators, these are the kind of smoothing things that are being performed, different kinds of operations being performed. Number of generations, maximum number of generations looked at is 100. This is a minimization problem being set, and based on that the very best smoothened value of the parameter are being chosen. So this is what comes as a part of fit smooth, right? Even if I type this again, I'm going to get error in guess. So fit smooth is actually not executed. There is some kind of error that is there as a part of the model. So the smoothing process is not happening. If it is not smoothened, then probably we can very well look at. I mean, if we have to see if the smoothing can be set by going ahead with the name of a parameter. We give some kind of a sigma to start with. Let's see if that is going to work. Instead of it searching for the sigma, if I give some kind of value of sigma, how will it respond? So that's one more thing that we can look at. It's taking some time for the fitment process. So this is how the smoothing process has been executed. You could see that there are stages: generation 0, 1, 2, 3, where the different possible values have been looked at, and after a couple of generations it has found that no significant improvement, and the solution fitness value, this is typically coming out to 1.13. That's the fitness value. If you see here, here also the fitness value is 1.13. This has been at 1.13 itself, the solution fitness value. The parameters at the solution, if you are looking at, this is 6.87. That's the best. 6.7181. That's the best kind of a solution. So that is how we are getting the values of the parameters. Solution found in the generation 1 itself. 3 generations have been performed, and that's the overall smoothness that has come up. Now I can very well check out this fit.smooth. If you look at the smoothened model, there's nothing much of a difference here, right? Even in this fitted model, so you could have gone with the initial fit itself. It's saying it's a probabilistic neural network. This is the data set on which it has executed. You don't find much of a difference. But the sigma value here, is an additional parameter that is coming where the overall smoothing of the model has happened. So we'll try the prediction both with the original model as well as with the smoothened model. The best thing that you can look at is here we'll use a function called performance, which is called PERF. We'll use this particular performance function called performance. So let me use question mark PERF. It's a performance of a probabilistic neural network. So I have to give these two inputs. I mean only the neural network. So I can give both the initial one as well as after the smoothing. Let's see what is the difference in the performance in the process. The function perf uses the holdout method. The method takes the training set using the function learn, iterates over each and every observation to guess the current observation with a reduced training set. So within the training set itself, it tries to partially build the model with some part and again test it with some other part. So that's how it's a kind of an iterative process that is going to do. So let's look at the performance of fit PNN, which is before the smoothing process. So or let me see after it, performance of it requires the neural network itself fit smooth. Okay, the performance it has taken as fit smooth. On the smoothened one, if you look at the performance, all else remaining the same, the performance of the smooth, this data set is the same on which it has worked, and a couple of other inputs, the couple of other output elements that you have to look at in this context is it is showing us observed values wise these are the ones that are actually negatives and positives, whereas the predicted wise this is how it has understood the positives and the negatives. Based on that, it is saying the success, there are 282 successes in the whole process, 113 are failures, resulting in a success rate of 71.3%. So this is what you could see after the smoothing of the model. But before the smoothing, actually I should okay, the NN is trained and smoothened probabilistic neural network. So I have to give only the smoothened probabilistic neural network, otherwise it will not accept the values. So that's the reason the base neural network I could not give to it. I have to give a smoothened probabilistic neural network itself. So this is what is the level of accuracy of this PNN when it is doing the test, when it is doing the accuracy test on the training data, which once the model is smoothened, we have asked it to predict based on the training data itself, and these are the predictions on the training data, and based on that we could see that the success rate is this much with a Bayesian information criteria or a kind of a error measurement value to the extent of minus 457. Now here there is a slight small difficulty. Right here the guess is a function that we are going to work with for the prediction purposes. Right? So let's understand what the guess is doing for us. It infers the category of a new observation. So that's how we will look at the guess. So NN is a trained and smoothened probabilistic neural network. So I can very well give the neural network after the smoothing. Whereas X I have to give it as a vector describing a new observation. So I can give only a vector that is describing a new observation. So that's the only thing that I have to give as an input in the testing data. So I have to give it as a vector. So let's give So if you look at guess, first for the first one, let's try to fit. Right, the model name for us is fit smooth. That's the name of the model, and the data that I have to take is the test data. I can't give the whole because it is taking only only the first one. I mean only one observation. So probably if I am setting it as the first row and columns wise, I want it to take all the columns except no. Let it take all the columns. So I'll take only the first row value. Let's see how it works. I'm doing the guessing only for the first row. It's an error saying the next one, the input that it requires, the data length 7 is not a submultiple or a multiple of number of rows. So otherwise, it's better that I convert this into matrix as dot matrix. I'll say test data, and I'll take only the first row of this data. Let me see if this works. No. Non-numeric argument to a binary operator. Otherwise, let me see. Let me just check if I omit the first column. Will it work? Yeah, I have to omit the first column, which is actually our category column. So I have to omit that column while supplying as an input to this. So what it is giving is, in case of the first one, it has given me that the category is positive and there is a 24% chance that it would be negative and almost 75.3% chance that it would be classified as positive. So this is the guess function which it would execute only for one record of data at a time. So this is where I have to loop this process and get the categories for each one of them separately. And this is where I have to take it into an array variable. So let me first create one array variable wherein I'll understand how much test data is there. So let me look at the dim of test data, so that I'll say 169. So what I'll do is I'll create a variable called pred, which is a dummy with 169. I'll create a 1 to 169 are the observations that the pred will have. So if you see the pred as a variable, if you look at it, it is 1 to 169, right? Now I'm creating a for loop for I in 1 to 169. So I want to repeat this process 1 to 169 times. For each thing, I want to look at it as pred of I. So a predicted value of I want to get computed, which is through the guess function. And the guess function will take bit smooth of this whole input I'm going to give to it. The only difference being, instead of taking the first row, it will take the ith row. So from this I'll get the ith row, and I will only pick only the category part. so that it will give me the calculation quite comfortably. So I'll get the pred of I as this one, and so let me take the predicted category of I, which will come out as positive or negative, and I'm closing this particular for loop. So once I do this, this is executed 500 and 460, 169 times. So now when I say pred, instead of 1 to this, now I am getting the numbers as positive, negative kind of stuff. Now I can very well go ahead with respect to the table wherein the predicted value is pred and the actual value is coming out from the test data $diabetics. So this is how it has worked out. Along the diagonal 75 plus 48, which is 123, is the correctness out of 169, resulting in an accuracy of 72.78%, which means the remaining is going as a part of the error. So we have created the predicted values, and based on the predicted values, so here we cannot do the prediction all in one single go. We are doing it stepwise. The guess function has done the predicted value for the first one, and we have put that in a loop and stored the value as a part of pred I. So initially we have given the pred I as a numerical value, and after that the same pred I has been improvised to get whether it's a positive or a negative kind of a group, and after that once we have compared it with the actuals, the on the test data the accuracy of the model was lying at 72.78%, which is indicating the remaining 27% to be an error in the process. So that's how you can use the probabilistic neural network, right? Let's see. We have looked at the performance statistics of the fitted model. Perf is the name of the function that we have used, and the smoothened model is what I have to give as an input to it. Based on that, I can very well assess the performance of the model, which will tell me on the training data, if it has to again use the model back on the training data, what are the observed values and what are the guessed values. Based on that, on the training data, we'll get a measurement of what is the level of accuracy and what is the level of error. Right, so we are getting the observed values, the guessed values, the successes, how many successes are there, how many failures are there, what is the success rate, and even the Bayesian information criteria on the training data we are getting. Then use the guess function to do the prediction for the first observation of the testing data. So use the guess function to do the prediction for the first observation of the testing data, and once you are able to once you are able to get the category of the same, you can use a for loop to repeat the process across all the records of the test data, and based on that get a prediction of all the categories from the test data, and after that you create your confusion matrix between the predicted values and the actual values. Based on that compute the accuracy rate of the model or even the error rate of the model. So that's how the probabilistic neural network can very well be used. Let's see if I can plot the probabilistic neural network. No, the probabilistic neural network is not getting plotted, so it's only what about the summary of the same. Neither the summary nor the plot. Summary wise, again it's the same summary, so there's nothing much of value addition that is coming through the summary. The plot does not work in case of probabilistic neural network. It's only using the model for the fitment purpose that we are typically doing. So this is also a kind of a model that you can try it out for your categorical data for the classification purpose. Then we'll move on to the next important algorithm, again doing the process of classification itself. Now let's move on to the next model, which is the multi-layer feed-forward neural network. This is also something that we are using for classification purpose. So for the same data set, we would be using the multi-layer feed-forward neural network as well. So what we will do is we'll use the package amor, and we'll use a function called train within that. So let's install the package. Install dot packages amor. Oh, sorry, I have to put it in quotes. Okay. The amor package is installed. Let's load the amor package. And now let me see what is there as a part of the learn function. Learn function, it also creates and or updates a probabilistic neural network. So even this, oh, this is there as a part of, sorry, it's not learn, I'm sorry. The function that I have to use is train. So the learn is a part of your probabilistic neural network. I have to talk about the train function. The train function, it's again a neural network training function. Oh, this is a neural network training function for a given data set, which is a training set. So I have to give a training set. This function modifies the neural network weights. So the weights that are given to each of the observations in the neural network, they are modified and biases to approximate the relationship among the variables present in the training set. So the weights are typically played around with. These may serve to satisfy several needs. So even if you want a non-linear functions to be fitted, it becomes more comfortable for the fitment process. Now let's look at the training part here. Initially, I have a neural network to train. Right, I have to give the neural network to train, which means I have to create a model of the type neural network. Right, so the net wise I have to give a neural network for the training purpose. So I have to create a new neural network for this particular purpose, and then the P and T, training set input values, training set output values. So the 6 different columns, they will go as P, which are the training set input values. T is the training set output values, which talk about whether the person is positive to diabetes or negative to diabetes. Then the P value is the validation set input values for optional early stopping. So if I want to stop early, I can give a P value and a T value. The error criteria, there are 3 different error criteria based on which I can work. One is the LMS, which is the least mean squares error, or I can go with LMLS, which is the least mean logarithmic squared, or I can go with TAO, which is the tau error. So I can go with any of the 3 different kinds of error criteria in the process. And if by default the report is true, which is saying that the logical value indicating whether the training function should keep quiet or should provide graphical or written information during the training process. So if it is true, you will get some kind of notes being supplied once you are building the model itself, If I am setting it to false, there's nothing that is displayed on the screen. So this is how we want to go ahead. The only thing, okay, we have the P and the T values with us already, but now we have to create the neural network that we really want to train. We have the training, we have the P value, which is the training set input values. We have the T values, which are also the training set output values. And we have the error criteria, which we already said we can try all the three: LMS, LMLS and TAO. We can get the report displayed, right? And we can also talk about the number of shows, number of times to report. If we want, we can get the number of times to report in the process as well. So we are looking at the error that is coming out in each of the processes for the understanding purpose. Now we can get started. I'll tell you how we create the neural network first. The creation of the neural network, actually a new neural network that you have to create, comes from a function called new FF, which is a new feed forward kind of a neural network that we are talking of. So let's use this function new FF to understand it a little bit more. So it's there as a part of the package called MOR, right? This is the one that we are using. Creates a feed forward artificial neural network according to the structure established by the MOR package standard. So initially, first I have to create this kind of a neural network, and then I have to give this neural network as an input into the train function. So the first one, I have to first create this kind of an input. But if you look at the input data, so let's see what it is typically containing. New FF. So the first input that I really require is n dot neurons, which talks about numeric vector containing the number of neurons in each layer. So the first element is the number of input neurons, the last is number of output neurons, and depending on how many hidden layers I am giving, for each of the hidden layers I have to give how many neurons, hidden neurons are there in each of the hidden layers. So I have to give the n neurons as an example, which means depending on the structure that I want to build, this can keep changing. So that's the first thing. Then the learning rate global, learning rate at which each neuron is trained. So I can give the speed. If the higher is the value, the learning is much faster and minute elements can get omitted. If the learning rate is if the value is much smaller, it is that the learning rate will be much slower. If you look at the process out here, the learning rate global, it actually constrains how much the algorithm is allowed to change the weights. So if I set it as 0.01, the weight can be changed only by the extent of 0.01. So if the current weight is 0.32 for a particular variable, it can either make it to a maximum of 0.33 or 0.31 in the next stage. So the learning is much detailed if we are setting a much smaller value, though it may take some extra time for the network to get trained, but there is a lot of detail in getting trained. Then we also give the error criteria in the process, right? Okay, the momentum global is momentum per every neuron. So for several training methods, I can give the momentum. Generally, we set it at 0.5. The error criteria, I can give any of these three different kinds of errors. So how close is the neural network prediction to the target? What is the way it will decide that a particular neural network is very close to its target? So that is what is the error criterion. We will try out all the three to see if there is some kind of a difference in the model: LMS, LMLS and tau error. So those three can very well be given as inputs. Then I can also give the hidden layers, the activation functions of the hidden layer neurons. If required, I can very well specify the activation functions for the hidden layer neurons. So we have a pure linear or tangential sigma, sigmoid, hard limb or custom. So we are having different kinds of hidden layers in the process. Output layers also I can have any one of these activation functions. So we can try all the combinations out here. And the method, the training methods, there are 4 different training methods that are supported, which is adaptive gradient descent with momentum, batch gradient descent, and batch gradient descent without momentum. Probably we may not be knowing mathematically how each of these differences are getting reflected, but what we can very well plan out is keep doing this process again and again with different values so that we can see in which case our output is coming out to be more and more appropriate. So initially first let's create one model with the new FF. So let me call net1. Let's say we'll do a 2 or 3 different kinds of models. So let me use new FF. The first thing, n dot neurons. I will set the n dot neurons as, so we have how many? We have 6 input neurons, right? And I will make it as 3 in the first layer, 2 in the second layer, and I'll put 1 output neuron. So that's how I want my number of neurons to be created. Then learning rate global, I want it to learn slightly slower, which is where I'll set it to 0.01. Again, this is a kind of a flexibility for me. Momentum global, I will set it to 0.5. Again, this is another area which I can play around with flexibly. Error criterion, let me call this as LMS to start with. But again, I can change it to LMLS and all the other stuff. Then STAO, which is in case it is tau, then I have to specify it. And because this is not tau error, I am specifying it as NA, not applicable kind of stuff. Then I can also give the hidden layer, I'll give some kind of activation function. Let's say I want to give sigmoid function for the hidden layer, whereas for the output layer I may want to try something else. So again, these combinations, let's say for output I want it as pure linear. Again, not necessary, you can try playing around all of them. And finally I'll also give the method any one of these 4. So let me just take it as adapt GD. And if I am giving it with momentum, yes, the momentum value also will be considered. Otherwise here the momentum value is not considered. So probably now you know you can very well change different kinds of models altogether. Now similarly, let's change one more. Right, in one of them, let me change it to GDWM, this is with momentum, right? And probably if required, here I'll just alternate it. Here I'll take, for the output, let me take sigmoid, and for the input layers, let me take linear, just for trying out different models and seeing how the overall result is going to come out. Instead of LMS, let's say let me try LMLS, which is the logarithmic, the second L that is coming out is for logarithmic squared errors. And let's say the learning rate, slightly let's speeden it, making it 0.05, and let's call this as net2. So like this you can create. So if your correct activation functions for the hidden layers. So otherwise let's set it to 0.01 itself so that all of them are learned at the same rate. Okay, hidden layers pure lin, sorry, I can't use it linear, it is pure lin. Pure lin is what is pure linear, right? I can very well go with global learning rate of 0.05, not an issue. Okay, so we have created net 1 and net 2, which are the two different models for the creation process. So now we are understood the creation of the neural network first. This part is clear for us. So multi-layer feed-forward neural network first expects that we create a neural network using new FF kind of a function, wherein I have to give how many input layers are there, how many hidden layers are there, and what are the how many nodes are there in the input layer, how many nodes in each of the hidden layers, and how many nodes in the output layer. And I also need to specify learning rate global. So by what extent the weights are going to change from iteration to iteration. The lower is the weight, the slower is the way in which the weightages are changed and various iterations are being done, and finally the best possible model is being selected. Error criteria, talking about different kinds of errors that we are using in the process. Hidden and output layers, basically talking about what are the type of activation functions I can give for both the outputs as well as the hidden layers. How do I transform them from one form to other? We have five different kinds of transformations that are available for each of the hidden layers as well as for the output layer. Then the solution strategy for converging on the weights. How do we converge on the weights? We have four different methods. One is the adaptive gradient descent or with momentum, or we can also look at the batch-wise gradient descent versus batch-wise gradient descent with momentum. And we can also set the method where the report equal to true, so that we will get a kind of trace of what has been performed during the process. Now using this, we got two models created. Now our data is, okay, the data wise, here I also require my data to be scaled. Just like any other neural network algorithm, I want my data to be scaled. So let me quickly look at the diabetes 1 that we have used in the beginning to see if this is already scaled. Yes, the diabetes 1 is already scaled data. So I'll use this diabetes 1 that we have created in the beginning, which is a scaled data which contains even the output as scaled as well as the input scaled. Right, I can very well use this. So we'll create a training data and the testing data on this set. So initially we'll set the seed as 1000. Then I'll create a variable called train, which is using the sample function. Right, from 1 to 564, we are picking up 395 values randomly with replace equal to false, no duplication in the process. So from there I am getting my train data, which is nothing but a subset of diabetes 1, which includes the rows that are there as a part of the train, and it takes all the columns. Similarly, when I am talking of test data, it's also a subset of diabetes 1, which takes the rows which are not there as a part of the train and all the columns. So I have a training data with me, I have a testing data with me. Now I can very well go ahead in terms of doing the fitment. So here you could see that there are n number of combinations of the models that get created. So I'll call it as fitnet 1, right, where I am using the neural network 1 for the purpose. So I'll say train. Now if you look at the model, what you have to give here, first thing it takes train. The neural network is something you have to give. So let me give net 1 first. That's the neural network that I am providing. I have to give p values and the t values. So let me take the p value from the training data. Right, I'll take the p values from the training data, the training set input values. Only input values I have to take. So from the train data, I'll take all the rows, I'll take all the columns except the seventh column. That will be my input values. Then T, which is containing my output values, that also I can very well take from train data. The output values also I am taking from the train data, all the rows and only the seventh column. So I have taken the output as well. Now I don't want p-value and p-val and t-val because I am not looking at early stopping of the algorithm. Error criterion, initially let me set it at LMS itself. For the first model, anyhow the error criteria is LMS, only in the second model it is LMLS. Then report, let me set it as true so that I'll get a trace of what has been performed during the process. Right, and again, if I don't show ensures, if I show ensures, it will show me the process for each of the number of steps, and show dot step is telling me each of the steps. So all these things let me not bother too much about. Right, I can do n number of steps in the process. So let me not go ahead with any other input values. I think this should be sufficient for me for the training process. Let me just see, and if required, I'll give some additional input. Okay, I think it requires n dot shows. So n dot shows is typically talking about number of times to report, and that too if the report is true. Now that we have set report equal to true, I have to specify number of times to report in the process. So let me just set n dot shows as 100. So I'll say 100 times you do the reporting process. Now let me see if the model is learnt. Now still we have show dot step. Show dot step, number of epochs to train non-stop until the training function is allowed to report. That is what I have to give a show dot step. Oh sorry, I can set n dot shows as 10, whereas show dot step I can set it to 100. Show dot step I'll set it to 100 because number of epochs to train, number of records to train non-stop until the training function is allowed to report. So what is the kind of a training process that has to typically get in? So it has shown 10 times LMS 65, 63, 62. You could see that LMS has come down over the process. It has come to the extent of 58.58 is the kind of error that has come in the process. Now similarly, let me try fitnet 2. Right, here itself let me try fitnet 2. I will use net 2 as an input. The train data will continue, the test data will, the training input, training output are continuing. Error criteria I can go with LMLS, and all other things I can keep them to be the same. So this is the fitnet 2. I am using two different models. So here I could see that 3097, 3079, and probably after a certain stage 3021, the decrease is very marginal. So this is how the model has been. The feedback from the feed forward from the model is typically improvising the model for each of the processes in this kind, each of the steps in this particular mode, which is resulting in improvisation of the model altogether. Now these two models that we have got, now I want to go ahead in terms of executing this on my testing data. Right, now I have the whole model with me. So if you look at typing the name of the model, first of all, to see what the model has given, fitnet 1, there are so many things that have come as a part of this fitnet 1. If you look at fitnet1, okay, these are the layers. So there is a $net. Within that we have layers. There are -1, -2, -3, -6. Then we have, so these are the input layers. These are the hidden layers. For the first hidden layer, these are the nodes, second hidden layer, and this is the output layer. Then we are talking about the neurons. In each one of them, if you are looking, the activation dot function is the second activation function, which is what is the sigmoid that I have taken. Then we are talking about, there are two different activation functions. For the hidden, it is the sigmoid function. Then you could see a few more inputs in terms of the parameter values. And the method that we have gone with is adapt gradient descent. So this is the whole process that has gone in terms of the first method. Now what I can very well do is use the first method, the name of the method $net. So if you simply say fitnet1 $net, if you just see this fitnet1 $net, it actually gives the entire model that got fitted. So this is the total model that got fitted. Now what I can very well do is I'll execute this model on the testing data. But the execution of the model, this one on the testing data, goes through a function called sim. We are trying to simulate the stuff. Calculate the value of the output values of the neural network for a given data set. So this is what typically goes. I have to give the neural network and the data set of the input values. So that is what will be executed through the sim. So what I can very well do is I'll say predicted value, where I'm using sim, and the model wise I'll use it as fit net1 $net. So this is the model that I'm using, and I'm taking my test data, and this test data should not contain it should not contain my output value. So I am putting it as -7. So based on that, there is a simulated value that is coming out for the predicted. Now look at what the pred is giving you. It is giving you the probabilities. The pred is actually giving you the probabilities. So what you can very well do is you can very well set the pred. If pred is less than 0, right, now you can say pred1, which is nothing but if else pred is less than 0, then set it as 0, otherwise set it as 1. That is the pred1. Now you can very well find out pred1, which comes out as 0s and 1s. Similarly, we have actual 1 also, which is already existing in our data. Now I can create table between pred1 and actual 1, which will tell me the matrix. So in this case, it has given me that 121 are correctly predicted, whereas 48 of them are errors. So this model again has given me a 71.59% accuracy when I am executing the same on the testing data. Similarly, I can try out my model 2 here, right? So now we can do the prediction with respect to fitnet 2, all else remaining the same. So we got a pred value. Then again I can create pred1 out of it based on the predicted values if they are less than 0 or greater than 0. Then I can very well create a table function to understand pred1 versus actual 1. Oh, this is given a completely different story. Pred1. Now if you see the pred1, Oh, pred 1 has actually given all the ones itself because this is a logarithmic. Let me just see how the output is working out here. In this case, the error rate looks like slightly higher. Let me just check it again. So let me go with the pred value. Yeah, here the pred values are coming out to be completely in the z. So I have to check it with respect to 1 here rather because there is a logarithmic. So the values have a logarithmic transform. So basically I have to set them with respect to 1 rather than with respect to 0. So as long in all the cases I am getting 10 to the power of itself, right? Either I am getting it as 1 or I am getting it as very heavy negatives. Either 1 or very heavy negatives is what is coming out in the whole process. So the overall this model is everything is getting fit as a part of 1 itself. All of them are getting positives, so the overall accuracy of this model is very is not up to the mark. Whereas in the earlier case, at least we have found that the accuracy of the model is much better. And there is no way I can even plot fitnet1. So we cannot plot the models that we have fitted even through this. The only thing is whatever the models that have got fitted, we are trying to test them out on the testing data, and based on that we are trying to see what is the level of accuracy or what is the level of error rate that is coming out after the implementation of the model. So that's the way out. We can go ahead in terms of using all these different kinds of algorithms of neural network for the classification purpose. So this is what I wanted to take up as a part of this session. I hope you got a broad, a good amount of overview regarding the usage of all these mechanisms. If you have any further queries, you can very well get in touch with me by giving me a call on the number that I have given below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.